For polyatomic ions, one electron is added to the Lewis structure for each negative charge, and one electron is subtracted for each positive charge. It does not matter to which atom you add or subtract this extra electron. For example, NH4 plus, nitrogen's in the middle. Hydrogen have one valence electron apiece. Nitrogen has 5. But since there is a plus charge on the ion, I'm going to subtract 1 from the nitrogen. And so the Lewis structure for NH4 plus looks like this. If I look at formal charge of hydrogen and of nitrogen, for hydrogen, 1 valence, nitrogen 5, and then we split these electrons evenly. So each hydrogen has 1 assigned, formal charge is 0. Nitrogen has 4 assigned, formal charge of +1. The total formal charge for the ion is +1, which is the same as the charge on the ion itself. When you draw the Lewis structure for SO2, you obtain 2 equivalent structures. It looks as if one bond is a single bond and the other is a double bond. Actually, the 2 bonds are the same. If we call this oxygen 1 and oxygen 2, you will see how it looks as if the double bond is switching between oxygen 1 and oxygen 2. What's happening is one pair of electrons is delocalized over the 3 atoms, and it's said to exhibit resonance. Resonance is where I can obtain equivalent structures simply by moving a double bond. What's happening in this compound is that double bond, those pi electrons, are continuously flipping between the different oxygen atoms. There are 5 general cases for which the octet rule doesn't apply. Anytime you see beryllium, beryllium is not going to have an octet. It's only going to have a total of 4 electrons. Boron will always have 6. So these are the 2 exceptions that are going to have less than an octet. Sometimes the central element has to have more than 8 valence electrons to accommodate all attached atoms. There are many exceptions under number 3. So I can't give you the central elements that are exceptions because there are several. I'm going to cross off number 4 and 5. Even though these do occur, I'm not going to give you compounds with D or F transition metals or species with an odd number of electrons. So we're not going to worry about those. So if I want to write the Lewis structure for BeCl2, chlorine has 7, and beryllium has 2. In the compound, beryllium only has 4, but that's okay because beryllium is one of those exceptions with less than an octet. ASF5, fluorine has 7. I'm not going to draw all the electrons around the F's. And arsenic has 5. So you'll see that in the compound, arsenic has more than an octet. It has 10, but that's in order to accommodate all the attached atoms. If an exception occurs, it's going to occur around the central elements. The terminal atoms, like F or Cl, will always have 8. When atoms join together, energy is released, and energy must be absorbed when bonds between atoms are broken. The bond energy is the amount of energy necessary to break 1 mole of bonds. For example, if I have H2 going to form 2H, the energy necessary to break this bond right here is 436.4 kilojoules. In a polyatomic molecule such as water, water has 2 OH bonds, Well, the energy required to break one OH bond is different than the energy required to break the second OH bond. In both of these examples, I'm breaking the bond between oxygen and hydrogen, but you'll notice that the bond energies are different. So bond energies depend on the environment, and it's customary to use average values. So the delta H value for OH would be 459 kilojoules to break that bond. Bond energies can be used to estimate the heats of reaction. The heat of reaction is equal to the sum of the bond energies of the reactants minus the sum of the bond energies for the products. So let's look at this example here. We want to use the bond energies to estimate the heats of reaction for this equation. Before we go any further, we need to know the bonds in these compounds. So we need to draw the Lewis structures for all of these compounds, so we know what bonds are present. C2H4 looks like this. It's got a double bond between the carbons and then 4 carbon-hydrogen single bonds. We have 3 oxygen. Oxygen has a double bond between the O's. We're forming 2 CO2 molecules. CO2 contains 2 carbon-oxygen double bonds, and then we have 2 water molecules. It's always a good idea to do the dots first. I'm just drawing the dashes to save some space here. So the heat of reaction, delta H, is equal to the sum of the reactants. So we have a carbon-carbon double bond plus 4 carbon-hydrogen single bonds that we're breaking plus 3 oxygen-oxygen double bonds. That's the sum of the reactants minus the sum of the products. Well, I actually have 4 carbon-oxygen double bonds that I'm forming plus 4 oxygen-hydrogen single bonds. Make sure you're paying attention to these coefficients because those do affect the heat of reaction. Then we plug in our numbers. Carbon double is 6O2. Carbon hydrogen is 411. And then oxygen double is 494. Subtract 4 times 799 plus 4 times 459. So the heat of reaction for this equation comes out to a value of negative 1,304 kilojoules. So the sum of the bond energies for the reactants minus the sum of the bond energies for the products. Bond distance is the distance between the nuclei of bonded atoms. Multiple bonds are stronger and shorter than single bonds. Comparing a triple bond to a single bond, notice it's going to take more energy to break a triple bond than a single bond. And the bond distance for a triple is a little bit shorter than that for a single bond.